So, hi everyone, I'm Kemil Naidoo. I'm the head of commercial interiors for TOT Architects, and I'm also a project lead as part of the life science team within TOT. Today we'll dive into the latest research that I've been doing with TU Dublin, and that research is on GPT BIM-enabled generative designs for Cleanroom. So we've been hearing quite a lot of the AI term being used, but not really seeing a practical use of it. So hopefully this paper will shed some light on a practical use of AI, let's say, in the industry. So just to summarize, hi Chris. So just to summarize what I'll be talking about this afternoon, so I have a quick, so we'll go through a quick introduction, context and problem that this paper has been addressing, why it really matters, the aim of the study itself. Also, there was an experimental research process framework that was developed as part of the research that was done with TU Dublin. And then we'll assess the research methodologies that was employed and why it was employed for this paper. And then we'll look at the evaluation of the data and the feedback from the industry experts. And then lastly, we'll be looking at the research findings and some of the technical and ethical barriers along the way. So a little bit of the introduction. So the semiconductor, the medtech, and the manufacturing industry and pharma industry in Ireland is quite a big part of the economic landscape, and that area is growing quite rapidly. So the research and development of clean rooms is another vital part of that ecosystem that is also evolving quite rapidly, and research needs to be done on how to optimize those specialized rooms. So the problem that we have is spatial planning is quite complex and slow. And there's no research that is combining the latest innovations in AI in parallel with generative design processes that we currently have within the BIM ecosystem. And then it's also a relatively new and unexplored area of research, which I think will be beneficial to the industry as a whole. And also it addresses the architectural challenges in clean room design. So for those who are not familiar with clean rooms, so they've been historically, the focus has been on the mechanical and electrical element of the design, and seldom the architectural is always an afterthought. So the focus for this paper, coming from an architectural background, was to look at the architectural element. How can we optimize it, and how can we optimize the whole design element of it, and then give us the architectural sector more time to really assess what can we change from an architectural perspective. So why does it matter? So current design methodologies and processes are very labor intensive and often quite unstructured. There's also industry demands. Like I said, it's a growing economic landscape. It keeps evolving. There's also the convergence of technology. So there's an opportunity here to integrate the latest innovation in machine learning, which is again a subset of artificial intelligence, with current BIM technologies. And lastly, it's to automate repetitive tasks and accelerate design concept and enhance collaboration and quality in that process as well. So the aim of this study at the time, the thesis really investigate how GPT models can be integrated within existing BIM-based processes, and including generative design to automate early stage spatial planning of clean rooms. And then that whole process was evaluated via expert interviews, and also there was a process framework that was developed, and then that was tested against a real project benchmark, a real life project. So what is GPT for those who are not familiar with the term? So it's generative pre-trained transformers, which is a group of neural network that forms part of the natural language processing. So it's also known as large language models, LLMs. So everybody knows ChatGPT. So that's one of the most common one that is being used commercially. What is generative design? So in a nutshell, generative design is a goal-driven approach to design that leverages automation so that designers can have better insights into their designs. make faster, more informed design decision, and also explore more design options using the power of computation. So, like I mentioned earlier, as part of the research study, an experimental research process framework was developed. So as part of this framework, it was a 4-step pipeline design. So what it essentially does, so it's a lot more complex. I'll try and condense that quickly within a couple of minutes. So basically at the onset of every clean room projects that we've been getting within the office setting and in the industry in general, you're given a set of documentation, usually in the form of the URS, which is the user requirement specification document. You also have the EIR document, you've got the technical guidance documents, and you also have the ISO standard documents 14644-1, 2, 3, and 4. So combining all of these documents together, so the design team's job is to extrapolate information from all of these documents and then convey, together with the process engineers, convey a spatial planning exercise that will then form the clean room design itself. So that is historically a very labor-intensive exercise, and the documents combined together end up being 300, 400 pages plus. So it's very taxing for an entity to do that exercise. So as part of this research, the plan was to use this information, insert that within a large language model, and using really careful and crafted nuance prompt engineering, extract only the relevant information from an architectural perspective that would inform the spatial planning exercise of the project. So once this, the relevant information is extracted, that information is then converted into either an Excel document or a CSV file. So once that's done, we go back into Revit. Based on that information, we set the boundary of the clean room. So that could be the space of this room or the entire footprint of this building. So once these two elements are set, then what we do is, as part of this framework, I've also created a Dynamo script. So the Dynamo script, which works innately with Revit, is the single part that automates the whole thing. So the Dynamo script's job in this instance is to use the static information that is being given within the Excel document that is extracted from the large data set. So Dynamo will take that static information and convert that into a graphical representation within the Revit environment. So it converts a static information into a dynamic information that you can then interact with. So the Dynamo script will use the CSV file that is inserted with all of the relevant information, and it converts that into a graphical representation. And what we do then, that graphical representation is merely a bubble diagram. So we're going all the way back to a rudimentary exercise, converting that into a bubble diagram. And that Dynamo script also works naturally with the generative design plugin that is in Revit at the moment since 2021. So that Dynamo script works with the LLM, and it also works with Revit. So what it does then, within the script's been designed that it works with the automation process in generative design in Revit. There's 2 steps. One is randomization and the other one is optimization. And the optimization within generative design in Revit works on the basis of genetic algorithms. So the best suited design is the one that's going to be, we are going to have iteration on. So using that process, you get the information from a static environment into a dynamic environment. And the Dynamo script has also a lot of nodes within them that allows for that bubble diagram to work the way we want it to work. So in some instances, they do overlap. In other instances, they operate independently from each other. And in some instances, they work in symbiosis with other rooms. Because in clean room designs, sometimes you have rooms that needs to operate in tandem with other spaces. So that's in essence how the process framework works. So once that was done, we looked at the research methodology. So for this instance, a dialogical action research method was used. The reason for that, because it is a semi-structured interview process with 2 rounds of interviews, which allows for a mutual understanding in identifying core issues from a both practical point of view and also from a theoretical standpoint of view with the industry experts. And it also allowed for the improvements within the process along the way. So once the framework was designed, we took that framework and then analyzed it and then showcased it to a panel of industry experts. And then feedback was given. So the feedback that we got from the industry experts, and as you can see from this table, the industry expert was on a broad spectrum. So the years of experience varied from 5 years all the way to 30 years of experience, and their field of interest, their field of expertise varied quite greatly as well. So you had architecture, you had end user in pharma, clean room, you had process engineer within the clean room industry, and you had also semiconductor clean room designers. So there was the main key themes that was extracted from the research itself was, one, the framework provided a digital transformation of the early design phase because it converted that static information into a more dynamic information. Then the conversion of the data from the URS, EIR, and other guidance document, it converted that into a digital and interactive data set that then, with the integration in Dynamo, improves the data analysis. Historically, you couldn't correlate all of the information together, but now with this framework, you had the potential to do that. There was also a shift from traditional process-driven design into a more multi-collaboration approach. It allowed for automation of labor-intensive processes, and the workflow for the translation of massive document data set, it converted that into actionable spatial layout design and enabled real-time parametric-driven design iterations.
2 minutes.
Yeah. So some of the ethical and technical barriers, obviously, is data privacy. Because clean room design is such a sensitive exercise, there's sensitive process flows happening. The data, the way the data set needs to be treated is quite sensitive. So not everybody is willing to share that process flow and the type of information that are usually embedded within these user requirement specification documents. The next one is the intellectual property rights. Who owns it? Is it the architectural practice? Is it the client? Is it the person who owns the Dynamo script, the framework altogether? So that was as well a point of concern. Design copyright, because it's been automated through machine learning and large language model, who actually owns the design copyright is another point of contention. And then design reliability as well. So who takes the fault for the design when it does go wrong? Also, some of the technical barriers, there's an unstructured, fragmented nature of the AEC industry. There needs to be more stringent guidelines by the construction and architectural governing bodies like the CIF or the RIAI. And also, historically, there's been a slow adoption of innovation within our industry. And lastly, which is the really important one, there's also a lack of clean data set to train domain-specific GPT models. So lastly, the research findings. So that was the experimental framework, and that was the case study. So when we benchmarked the experimental framework against a real-life case study that we used in 2024 within the office, so the level of accuracy was 95% and above for that one particular case. And when benchmark, it reduced the workload from the design team from a 4 to 5 weeks lead time to down to 15 minutes. And that was only on that particular project. Since then, I've been testing the framework on several other projects, and the accuracy level is 91% and above. And the number of iterations, the cut down time varies significantly from 15 minutes all the way to 3, 4, 5 hours. But again, quite significant because it's not weeks. And the number of iterations depends also on the computing power that you have. So for this particular experiment, we used 2 GPUs, NVIDIA Quadro, run in parallel to generate 40 iterations within 15 minutes. But some iterations goes beyond that, 200 iterations, 300, 400, and it can take hours. Thank you, and hope you have a few questions at the end.
Perfect. Thank you very much. Thank you.